This is the third part. Mutases. Mutases are those which help in the formation of PGA, that is 2P. From mutases are the isomerases, since it is a type which will cause the shift in position of one group of carbon from one carbon to another. Now in the example we see phosphoglycerol mutases. Phosphoglycerol aldehyde, that is 3-PGA, and acted upon by mutases to form 2-PGA, that is change in position of a group from one carbon to another. Ligases, these help in the formation of covalent bond. Energy will be required in the formation of ATP here. Example, CO2 plus pyruvate then acted upon by ligase pyruvate carboxylase forms oxaloacetate. Pyruvate is a 3 carbon compound and acetase is a 4 carbon compound. In biotechnology, ligases are called as molecular glue because help in the joining of DNA fragments. Every enzyme has a 4-digit number, earlier also done, called as enzyme commission number. Now first number in the figure indicates the category of enzyme. Suppose the number is 3133, anything it could be, but then the category would be hydrolase because the third othylyl, OTH is hydrolase. So third, you cannot also not change the number of the groups. These categories have to be remembered by with the number they correspond to. Now another topic is Km constant, very important topic. It is also called as Michaelis-Menten constant. It is a substrate concentration at which the velocity of enzyme catalyzed is equal to half of its maximum value. That is, it is that concentration of substrate at which velocity is its half. In common, the maximum velocity that can be attained in the reaction halves is obtained when the concentration is Km. Okay, Km constant is not numerically equal to half Vmax because it will depend on the affinity of enzyme for substrate. Affinity of enzyme for substrate is inversely proportional to Km. Now, in common sense, velocity depends upon Km. Now, whatever will be the Km, it will correspond to the half Vmax, and Km is inversely proportional to the affinity of enzyme for substrate. Maximum is the affinity, lower is the substrate concentration at which velocity would be half. Common sense. Since it is having low, so it would be low also. Now, if affinity of enzyme or substrate is high, the velocity catalyzed reaction will be fast. Common sense. Now, see, this graph is very important graph. Here in the graph, A is that when the enzyme is fixed, and B it is without enzyme. Now try to understand here Km concentration, so definitely V, it corresponds to the half V. Now and without enzyme, that is fixed enzyme, the reaction would occur as it should occur, but with enzyme the substrate construction concentration would just keep on increasing, and so would the velocity. Okay, now even in less velocity the reaction would be very fast. Here enzyme is fixed, so velocity would be very high, reached very high in very less substrate concentration, but without enzyme more substrate concentration would be required for more velocity. You see here in less substrate concentration A has reached to maximum point, but here even at this B, that is with graph of without enzyme, it has reached only here. Now to study Km we get a hyperbolic curve like something like this. Greater the affinity of enzyme of substrate, lower will the Km, since inversely proportional. Low Km will favor the reaction. Low Km favors the reaction, and low Ki, we will learn it in the next or few videos. Low Km will favor the reaction. Why? Because since low substrate concentration and with the enzyme low substrate concentration, so less energy would be used in the formation of substrate. So less substrate, even then velocity of the reaction would be fast and things would go faster. Now, suppose there is an enzyme protease question. It acts upon three different proteins: albumin, that is egg white; casein, that is milk protein; soybean protein. Now, the Km for these three different proteins will be same or different. It would be different because the proteins are different. For different proteins, the affinity for enzyme would be different. So, affinity of enzymes is inversely proportional to Km, and so Km would be also different. Now, some enzymes are called allosteric enzymes. They do not follow Km constant, but they show sigmoid or S-shaped curve. So, if question ask, there is an allosteric enzyme, now will it follow Km constant or not? No, it won't. It will follow S-shaped curve, and the Km following would have show hyperbolic curve. Now, what is activation energy? This is again an important topic. Activation action is the substrate that me. Hello. Substrate and activation energy is that energy which is required to start a reaction. For example, this is energy. Simple. It is potential energy means difference in the energy. Commonly energy, this y-axis, and x-axis is the progress of reaction. That is how the steps continuing in the reaction. Now, energy level of the substrate is fixed. It would be simple. Okay, throughout the progress of reaction, it would be constant. Now, product stage, the energy is very low, and at the transition stage the energy is very high. Now, for the reaction to take place, substrate must first bind to the active site of the enzyme, common sense, already read, leading to the formation of enzyme substrate complex. It is an transient phenomenon, that is, it is temporary. At this state, a new structure of the structure, this is called a transition state, because here that is electro here that is enzyme substrate complex when is formed, then the energy is very high, because then it would form this enzyme product, and this is the time where very reactions are forming. Okay, after the expected breaking of formation of bond is released from the enzyme, then the energy difference between substrate and products is different. Energy level of substrate and products become different, because here the enzymes are taken, and then here the products are formed, so energy difference will occur. Now, if energy level of the product stage, that is when the energy is the products are formed, is lower than the energy level of the substrate stage, that is in the transition stage, then the reaction is exothermic or exergonic. That is, energy level difference between substrate and called activation energy. This is the activation energy. You see here, substrate level, that is the common energy level of the substrate, that is how the things are going without enzyme, and there's the reaction, and then the energy that is required to let the reaction happen actually is called transition state. With the enzyme, this energy is less energy is required. So if question is asked that with enzyme will the activation energy more or less, it would be less energy would be required if enzyme present. If not, then the common level of the energy level of the substrate, and the energy level that would be required to start the reaction for initial stage, the difference between these two energy levels will be called activation, and it will be more than without enzyme. Okay, in the without enzyme it will be more. Now again there, activation energy is a barrier which has to be overcome for to start the reaction. Already told, enzymes are called biocatalysts because they accelerate the rate of biocatalysis by lowering down the activation barrier. This activation barrier. Now, in exothermic reaction, already told this today. In exothermic reaction, the external supply of energy is formed in the heat, and this is okay, and these reactions will proceed spontaneously, and there will be release of energy as product is formed. Now this is the another endothermic reaction graph. This is simply exothermic reaction graph. That is the exothermic means energy released is more. Okay. Now this is endothermic product. Energy is more than the substrate. That is product stage has more energy than the substrate stage. That is, here you see here the product has the energy at the peak point of product is more than that of the there is more than in the reaction. Changes occur in the free potential energy will take place, that is changes in potential energy take place. This is called as delta G. Exothermic G delta G is negative, that is the from final minus initial is negative, and in endothermic reaction final minus yeah, this final minus initial is positive. Okay, now again this if you see here activation energy without enzyme simply the main bigger graph is shown again here. The difference is the product says here had more energy, here as having lesser energy. Here is sorry, here it was having lesser energy because it is closer to the x-axis. Here it is having more energy as compared to the last one. This was all that I had to say. Now, factors affecting enzyme energy. Activity of enzyme is affected by conditions which can destroy the tertiary structure of enzyme. They are factors which can change the effect of enzyme. Which of the following factors can affect the enzyme? Substrate concentration, yes. Enzyme concentration, yes. Product concentration, yes. Temperature, yes. pH, yes. Activation energy does not, because activation energy won't affect because it is required only to start the reaction. After the start of the reaction, that is when the reaction actually is happening, enzyme has no lena dena with the activation energy. It was done to start the reaction. After the start, what would matter that enzyme's effectiveness and enzyme would depend on the activation energy. Okay, now first one, substrate concentration. What would the change be on the enzyme activity if substrate concentration increase? Now, if the substrate concentration increase and enzyme concentration is constant, then limiting factor is enzyme here. Since enzyme is fixed, so at this point all the enzyme molecules are saturated with the saturated. They are not free to act. Okay, so there would be like it would just be simply like enzymes would be more effective on more substrate and less effective with less substrate concentration. What would be the change in if enzyme concentration? Okay, enzyme concentration when increase, it will definitely increase the velocity. Enzyme concentration will have very good effect on the velocity. Since enzyme is responsible for velocity, it becomes faster or slower. So but then again at a point it becomes constant. See, it will just keep on increasing, keep on increasing, but then again at a time, since it is biochemistry, so at a time it becomes saturated, it won't be. Then again if you try to increase enzyme concentration, it won't help. Third is product concentration. If product concentration increases very much high, that is if products accumulate at site of reaction, that is okay, enzyme substrate here, enzyme substrate complex form, then enzyme product complex form, and then products get removed from the enzyme. Now if these products accumulate at the site of reaction, that is here, that is active state, it will not become free, keep on just formation of lot of products, and the enzyme won't be free for the other substrates to be acted upon by it. Okay, so it will remain enzyme product complex forever till the time goes. Now so the rate of reaction will slow down because it had to now keep gain again have more substrate, but then it is formed in the third stage, that is enzyme product complex. So then this reaction will slow down. Now coenzymes here, not enzymes, here coenzymes help in the functioning of enzyme by removing products of the reaction. That is, for example, if NAD is here, that is a enzyme product complex, then coenzymes act upon it and then form assimilated power, and this helps in the functioning of enzyme since it removes the products out of it. So now if we have to plot a graph, then what we would do is, since it is a product enzyme, since it is becoming more, then the velocity of it would decrease. With the more and more product concentration increases, more and more product concentration increases, lesser will become the velocity of the reaction, since it will become forming uh, electron product complex, so it won't be able to have more substrates, so reaction ultimately slows down, so fall down in the velocity as product concentration increases. Now next, yes, if the product composition keeps on accumulating at the site of reaction, then sometimes the reaction even becomes reversible. Okay. Now D, that is here, temperature. Temperature effect has very big effect on this. Enzymes are generally thermolabile, that is affected by temperature concentration. Simply, enzymes generally act as at optimum temperature. Generally corresponds to the temperature of the body, that is 37 degrees Celsius to 40 degrees Celsius. More is the temperature, then more would be the velocity increasing. But then again, after some temperature, that is more or anything less or more than 40-37, that the enzymes are not very effective. This concept is used in the preservation of food in the cold storage, that is 0 to 4 degrees Celsius. Of course, here the enzymes will be very inactive now, and the tertiary structure is not destroyed, but it is not functional. One very important thing, okay, that other factors, when increased or decreased on very large scale, then they destroy the function, the structure of the enzyme. But here temperature doesn't destroy in the, yes, 0 to 4 degrees Celsius. It just becomes not unfunctional, that is lazy or something, non-functional for some time. If temperature is more than 40 degrees Celsius, that is more than body temperature, the enzymes start becoming denatured because tertiary it is destroyed. Then they start becoming destroyed. Now cold-blooded enzymes are called poikilothermal because during winter they go hibernation, enzymes become inactive. In summers they will go estivation. Now in temperature range between 0 to 40 degrees Celsius, the velocity of enzyme catalyzed reaction is doubled every 10 degrees Celsius in temperature. For example, at 10 degrees Celsius there was x velocity, then at 20 degrees Celsius there would be 2x velocity, again at 40 degrees Celsius there would be 4x velocity. Okay, simple as that. Now next, yes, next, enzymes are generally thermolabile. Okay, already written also here. Enzymes are generally thermolabile. Now, but some enzymes are thermostable. Here it is a very important thing again. Now, thermostability is a character of enzyme present in the philic organisms, that is temperature loving organisms present in hot water springs. They are functional even at 80-90 degrees Celsius. Example is Thermus aquaticus. It is from this we get Taq DNA polymerase. It is nothing but an enzyme, Taq DNA polymerase, since it is having A's, so it is a enzyme, Taq DNA polymerase. This enzyme will be best functional at 72 degrees Celsius. It is not denatured even at 90 degrees Celsius. The body enzymes of human body are easily denatured after 40 degrees, so they can't survive. But this enzyme, that is Taq DNA polymerase, um, does not works very functional at 72 degrees and does not denature even at 90 degrees. It is used in the PCR, that is polymerase chain reaction, to amplify genetic material. Enzymes, now E, enzymes are generally function at the same optimum temperature. Okay, this is nothing but pH. Temperature was, A was what? A was product concentration. B was what? Yeah, B was enzyme concentration, third was product concentration, D was temperature, and E is pH. Enzymes generally function at same optimum temperature, but different enzymes will have different optimum pH. Now here more is the pH, then again, so it was same as velocity, same as temperature. pH increases, the velocity would be maximum at the point. Then again, if you more increase the pH, that is becoming basic, then the velocity starts decreasing. Yeah, okay. Now pepsin has best working on pH 2. Salivary pepsin since in stomach. Now salivary amylase works at pH 6 to 8, that is in our mouth, common sense. not basic, nor acidic in our mouth. Again, then trypsin works at pH 8. Now, the food enters the stomach at pH 2. Action of salivary amylase stop at pH 2. The salivary amylase will be denatured. Okay, since salivary amylase also goes with the food, which you that saliva also goes inside, and then it gets